The simple picture of a black hole, a dark sphere surrounded by a glowing disk, turns out to be as incomplete as a map that only shows coastlines and ignores everything inland. The environments around black holes are among the most physically extreme, most energetically productive, and most poorly understood regions in the universe. And the more precisely we observe them, the more layers of complexity keep appearing beneath what we thought we understood. Start with the accretion disk itself. The standard model describes infalling gas forming a flat, rotating disk around the black hole, heating through friction and magnetic forces until it glows across the electromagnetic spectrum. That picture is real but incomplete. Observations from missions including the X-ray Multi-Mirror Mission, XMM Newton, NASA's Chandra X-ray Observatory, and the Nuclear Spectroscopic Telescope Array, NuSTAR, have revealed that accretion disks are turbulent, magnetically structured, highly variable environments where the gas does not flow smoothly inward, but churns through magnetic instabilities, driven by a process called the magnetorotational instability. This instability is the actual engine of accretion. In a conducting fluid like ionized plasma in a magnetic field, the field lines connect inner and outer disk material, rotating at different speeds. The field lines stretch, transfer angular momentum outward, and allow material to fall inward. Without this process, nothing would fall into the black hole at all. The disk is not a simple pressure gradient. It is a magnetically driven engine operating at scales from the event horizon outward. Above and below the disk sits the corona, a region of extremely hot, diffuse plasma at temperatures reaching billions of degrees. This is far hotter than the disk beneath it, which should not be physically possible through simple heating. The corona is the source of the hard X-rays detected from active galactic nuclei and stellar mass black holes in binary systems. Its exact structure is still debated. Some models treat it as a compact region very close to the black hole, others as an extended atmosphere above the disk surface. Reverberation mapping, measuring the light travel time between corona and disk, suggests the corona in many systems is extremely compact, possibly just a few gravitational radii from the event horizon. Then there are the jets. Many black holes, particularly supermassive ones at the centers of active galaxies, produce relativistic jets, narrow beams of plasma and magnetic field launched perpendicular to the disk at a significant fraction of the speed of light. The jet from M87, whose base was imaged by the Event Horizon Telescope in 2019 and 2023, extends for thousands of light years. The mechanism by which these jets are launched is still not fully resolved. The leading candidates are the Blandford-Znajek process, in which the spin of the black hole itself extracts rotational energy through magnetic field lines threading the event horizon, and the Blandford-Payne process, in which magnetic fields anchored in the disk drive material outward from the disk surface. The relationship between jet power and black hole spin is a major open question. Some observations suggest more rapidly spinning black holes produce more powerful jets. Others produce only disk-driven winds with no clear jet at all. The physical condition that determines whether a black hole launches a jet, rather than just a wind, is not definitively established. Winds and outflows add another layer. X-ray spectroscopy has detected ultra-fast outflows from accretion disks. Gas launched at velocities up to 30 to 40% of the speed of light, carrying enormous amounts of kinetic energy away from the system. These outflows can heat the surrounding gas in the host galaxy, suppress star formation, and regulate how galaxies grow over cosmic time, the AGN feedback process. Models of galaxy evolution that do not include these outflows fail to reproduce the observed relationship between black hole mass and galaxy properties. In 2024, XRISM, Japan's X-ray imaging and spectroscopy mission, began delivering high-resolution spectra of active galactic nuclei that resolve individual emission and absorption lines with precision previously impossible from space. These spectra are revealing the velocity, temperature, and ionization structure of disk winds and corona in ways that will directly test competing models. What connects all of this is that a black hole is not just a gravitational sink. It is the nucleus of a multi-component engine: disk, corona, jet, wind, magnetic field. each interacting with the others in ways that feed back into the galaxy surrounding it. The simple picture lasted because it was all our instruments could see. Better instruments keep revealing that what seemed like background detail is actually the main story. Follow for more frontier astrophysics explained without simplification. And tell me, now that we know black hole environments involve magnetic engines, ultra-fast outflows, and jets that shape entire galaxies, does the black hole feel more like a destroyer to you, or more like a cosmic power station?